experimental data that people found. Just to point out that this reconstruction in the depth direction in the plane spacing. So this is reconstruction in D, right? D is the in the plane spacing. So this is surface expansion. It expands by 7% in the case of nickel. It expands twice as much in aluminum, right? So this is hard data that people discovered. And then if you, okay, so allow me to go back to this one here. If you look at, for example, this BCC structure, people also find reconstruction. People also find the 100 plane, right? So here, reconstruction in the 100 plane, right? And the, what is 100, the number density, okay, it's very easy to figure out. The 100 is just the surface density is what? Is A divided by A squared, 1 divided by A squared, right? Because you just look at this plane here, this is the 100 plane. Right? That would be my 100 plane, and there's no middle atom anymore. There's just 4 corner atom, 4 corner atoms multiplied by 1 quarter, you get 1. That's why you have 1 divided by A squared in that sense. And then you can have reconstruction in the D spacing, right? So again, you have surface reconstruction. And you have, for example, you have 0% in iron, negative 7% in tungsten, negative 12% in moly. Okay, so this is again hard data. So here you have surface contraction. In the other case, you have surface expansion. So you have contraction. Right, the in the plane spacing actually compress closer together as you terminate your crystal. Whereas in the other case, the crystal actually expand in that case. You have expansion in the first case, you have contraction in this 100 plane. And of course, the expansion, the reconstruction, interlayer reconstruction is different depending on which plane you're talking about. So this is in the Z direction, expansion and contraction. You have also lateral reconstruction that we talk about, that the atom in the plane actually move around in that case. Okay. Let's talk about the other closest packed structure that perhaps people are familiar with as well. This is the hexagonal HCP, hexagonal closest packed structure. You pack it as AB, not like ABC, as in the FCC structure, phase center cubic, or cubic closest packed structure that often referred to. And HCP, of course, what are HCP example are like this, are graphite, for example. So these are some of the example of the HCP structure. But the famous one is, of course, graphite, right? Because that's the lead in your pencil. That's graphite, and they pack like this: ABC. They're packed in a layer structure like this. Titanium, cobalt, they are all HCP structure, and these are the various plane that you have. And one interesting thing about these planes is that they are defined by 4 axes. So A1, A2, A3, like this, and then the C axis, like this, along the plane like this. So sometime when you see 4 index, that means you would have an HCP structure right away. And when you see a bar on top, that means it's negative 1. 1, 0, negative 1, 2, right? If you define this plane. that's 1, 0, negative 1, 0, like that. And this is 0, 0, 0, 1, like that. Okay. And to figure out this one, surface density is relatively easy. If I figure this one out, the surface density for this one is 1.15 divided by a squared, and the other one is more trickier to deal with. Sometimes you also see people write this mu index into 3 number instead of 4, and the notation is like this. The notation, just so that you know when you read some literature like this, notation is like sometimes you see h, k, and l, and this is equal to hk stay the same. This is equivalent to, if you see 3 index to represent XCP, usually it can be expanded into 4 index into hk stay the same, and then the third number is usually negative h plus k, like that, and then L is the last one. So the third index is like this plus this. Take the negative of that, that's negative 1. This plus this, take the negative of that, is negative 2, right? So that's the translation. Sometimes you see people write XCP, hexagonal Kohl's-Square structure, by 3 index. You can make it into 4 index, which is more transparent because the vector, you can see the vector how it goes.
So, but how do we visualize the negative intercept?
Yeah, so usually they write negative, because meaning that it's in the opposite direction of the other 2. Usually that's all that means. Right? So for example, these 2 is in the opposite direction of the third one, like that. Right? So that's a way to generate the 4 index XCP. Sometimes you see most people use this one. Sometimes people use this one. It's because they figure you can generate the middle, this one, by the first 2 anyway, once you know this rule. Okay, so it's not a big deal. Okay, so that's almost so that's XCP, AB type structure.
What do you mean about AB?
Yeah, so AB means that when you stack your layer, you put the second layer in between the spacing of the layer. Okay. So it's a little bit hard to explain without my prompt. So next day I'll come back and explain this AB structure, because it's really related to hexagonal Kohl's-Square structure, depending on how you pack your material. So if you forgot about that thing. But before we close, let me just finish up here on the other structure, diamond structure, very important crystal that we have. So you have carbon, silicon, germanium. They are all diamonds. They could have diamond structure. Carbon, of course, also has the graphite structure. Carbon, of course, has the C60 structure. So there are 3 different structures for carbon: graphite, and the XCP structure, the diamond structure, and the C60 structure for carbon. And this is the diamond structure. So it's kind of like you have the FCC structure, face-centered cubic, and inside you have a tetrahedron inside, in the tetrahedron form that you got. Okay? And so if you cut your plane along the red direction, you see something like this. You see the 111 plane. This is unreconstructed. You just cut along this red line. You see the 111. But in reality, what I want to show is that they could reconstruct into a 2x1 reconstruction. So some of these atoms could move closer. For example, these 2 move closer, and these 2 move closer together like this. These 2 move closer. These 2 move closer, and opening a gap